Hello everyone. Welcome to another Math Club talk. This is a special lecture by Professor Apoorva Khare from IISc Bangalore. We are extremely glad to have Professor Khare here. He did his BStat from ISI Kolkata and then went on to do a PhD at U Chicago. He has held positions at UC Riverside, Yale, and Stanford, and is currently a professor at IISc Bangalore. He specializes in a wide variety of topics from analysis to combinatorics to representation theory, and he'll speak about gram matrices today. Over to you, Professor.
Yeah, thank you for calling me here. Sorry for the delay. Several factors, but in part because that's not. Okay, so I'll start with maybe let's see. So which way does it go? Does this go up? Oh, it does. Okay. Okay, so the idea is to talk to you about gram matrices and a bunch of different ways that they show up. So first of all, I think we all know what gram matrices are. Let me remind you of the definition. So above first, okay, fine. The gram. So the gram matrices are what? So what's a gram matrix? So if you take vectors in, okay, I'm going to follow very carefully some write-up so that I don't mess up symbols in notation. So if you take the gram matrix, let's say the gram matrix of vectors, if you look at say y1 to yn are vectors, and these are vectors in some Euclidean space, and I will call it r to the r, sounds like a weird choice of exponent. The gram matrix of this is, let's say, I'll call it gram of yj. And what is this? This is the n cross n matrix. And what's the ijth entry? The inner product, right? So this is the gram matrix. So okay, great. Because these matrices have okay. So let's see. So there are lots of properties of these matrices. Maybe I'll start by the first one is that such a matrix. So every such matrix is positive semi-definite, right? So I don't know what to call this. Lemma, fact, lemma. How do these talks go? Do people prove stuff in these talks? Not. I'm not saying this particular thing, but do people prove things in the talks, in these special seminars or whatever? People do. Okay, fine. Okay, so yeah, so gram whatever. So gram of great. So so for all choices of yj's. So I think this everybody has proved, you said. Okay, good. Very good. Let's see. So what else do we know? How about the converse? Let's say over real numbers. Has that been proved as well? No? Yes? Every PSD matrix is a gram matrix. And this is part of the abstract that I gave you, right? So, but every positive semi-definite matrix is the gram matrix of some set of vectors. This is n cross n, then there are n vectors. So let's see if I say n cross n matrix, then there are of n vectors. And not only that, if I tell you the rank of this matrix, then you can take those vectors to be in R to the rank, which is why that R for rank. So that's what it is. There are several ways to see this. One of them is that you can, so maybe I'll call this a proof or a sketch of a proof. So let's see how would you prove something like this? Well, I would say let me give that matrix a name. Let's call it A. So you can write down A as B transpose B. write A as B transpose B. Let's see. So this is n cross n. I can of course write it as r cross n and n cross r and r cross n. But let me even be simpler. Let's do even something even simpler. Write n cross. Okay. So B transpose is of course n cross n. Why is this? So how would you write such a statement? Okay, you could do spectral decomposition, right? You can say that by the spectral theorem, A is u transpose du. Yes, and then right. So since the entries of D are positive, because positive semi-definite. So yeah, so that's you need to know properties of positive semi-definite matrices, which is that every one of them, every real symmetric matrix is of this form. Positive semi-definite if and only if the eigenvalues are non-negative. So that means this can be given a square root, and so you can just write B equals B transpose equals U transpose square root times. So you could do this, and then therefore A equals B transpose B or just B square. That's the same thing, right? And then what to do is now once you have this thing, then let's write down the columns of B as the bias, I guess. So let B equals y1 to yn. Sorry, not this way. The columns. Then B transpose as rows as the Y transposes, and then the ijth entry is precisely yi transpose and then yj. Am I doing this correct or am I doing this wrong? Is this okay? Okay. So therefore, this is the Gram matrix of those Y's. Great. So that's another property, another way, another synonym for Gram matrix. And I think you've probably all seen the fact that covariance matrices are the same as PSD matrices. And every covariance matrix is PSD, and every PSD matrix is covariance. Yeah. So therefore, that is that Bond and Bourne part of the abstract. That all these things are the same thing. Okay, but that was not what I wrote down here to start with. So now let me write down the lemma. Maybe lemma 2 or something. And this is the fact about when the Gram matrix is singular. So it's always positive semi-definite. So all the eigenvalues are non-negative. When is there at least one zero eigenvalue? Right? So the Gram is singular if and only if the yj's are linearly dependent. That's the statement. How does one prove this? These are all sort of not very hard to prove, but let's prove this. So I don't know. No, let's do the other way first, because the other way is even I can see the proof right now. So when I can see the proof, then I should do this first. Okay. So how do you prove this? So suppose to say summation Cj Yj is 0. Then what do you do? Take dot products. Right? Yeah, take dot products, and then therefore you should get and now if you just use the multilinearity, then this is just right for all I. And then, but that's just the Gram matrix. Right? So this is something like maybe C times the Gram matrix, or I mean C transpose times the Gram matrix. Yeah, or anyway, the point is, maybe I'll do the following. I'll say Gram matrix times C equals 0. Because anyway, this is a symmetric matrix. So whether I write this times C is 0 or C transpose times this is 0, it doesn't matter. I'm just taking real, so everything is symmetric and there's no problem. Fine. So yeah, so that's one way. Clearly it's singular with C non-zero. What's the converse? Suppose it's singular. So meaning, so say C times, suppose this matrix is singular, which means there is a vector which is non-zero, such that this happens, then sorry again. Okay, can you not take coordinates? Well, actually I'm cheating because I'll say something without coordinates and then eventually I will take coordinates. Huh. That's the one I was looking for. So if something is zero, then C transpose will also give you zero. Whatever times C is zero. Understood. Okay. But what is this? Yeah, so let's expand this out. This is where you do take coordinates and you get Ci, Cj, and then the gram matrix Yi times Y. So that's Ij then. This is zero. And now? Yeah, now this is because this is real, so everything is bilinear, not conjugate linear, it's bilinear. No, not just conjugate linear. So what you get from here is that it's, yeah. So summation Ci Yi and summation Cj Yj, which is the same thing, right? So you just get the inner product of this vector with itself is zero. But what is the, let me still use J's because mostly we are using it. What is the inner product of a vector with itself? It's precisely the norm square. And that gives you linear dependence, right? So clearly we are done. So that vector is zero, C is non-zero. Said something. Okay, so that's why. Okay, is this clear? If anything is not clear, obviously just ask why. Okay, now why did I say this? Because now from here, from this, we are going to say that gram matrices are basically at the heart of GPS triangulation. So what is GPS triangulation? So we are going to say that this simple lemma is going to be applied once right now and once at the end of the lecture. For now, the first application is to GPS. So the idea of GPS, as far as I understand it, which is very basic, my understanding is very basic, is the following. So suppose the idea is you know there's a point on the earth where your phone is, if you will, and there are some satellites in space wherever, and what the satellites can track, they don't know where the point is, but they know how far away it is, right? So they can track the distance. And so the question is, what is the smallest number of satellites you need to uniquely determine the position of a point in space or on the surface of the earth, right? So for example, let's just look at 2 dimensions. So I have a point in flat land, in plane. Okay, I have 2 satellites, let's say. Suppose I know the distance of the point from these 2 satellites. Does that uniquely determine the point? There's 2 choices, right? Why are there 2 choices? Circle. Exactly. That's it. Exactly. Many people said circle. So yeah. So okay, since I can't draw very well, let's assume these are circles. So this is one of those points. This is the other point. So there are 2 points, and both have the same. If I could draw better, this would actually look symmetric. So then, but the moment you have 3 points, and let's say the 3 points are, yeah, then if you have 3 different points, and the third point probably should not be on this line or something. Anyway, then it's very clear that, okay, as long as the distances are different, 3 points uniquely determines a point in R2. So the same thing for R3, which is, of course, if you have 3 points and you know which hemisphere the point lies on. So if you have 3 points, 3 satellites, and you have your phone, then that will determine something like maybe 2 choices of the points on the earth or something. But the moment you have which hemisphere of the globe you lie on, then you're good. But let's say we don't want to do that even, we want to do something like this. So if you have 4 points, 4 satellites, then it's pretty much done. So this lemma that the application of that lemma is going to be the following, which is the following. So it's going to be GPS, but let me tell you GPS in in R dimensions. Yes, always R dimensions. So so yeah, so application of theorem, and the theorem is basically suppose y. So yeah, so suppose I still have the same vectors y1, y2, yn in R to the R, but they are linearly independent, just like that there. Suppose these are linearly independent. Okay, then and sorry, comma, and y is a linear combination. So y belongs to span of the yj's. So I have some point in the linear combination of these guys. But then y is uniquely determined by, again, we need, so in R3 we need 4 points. So if they are linearly independent, then of course we need, suppose even they were all a basis, then that would mean there are many points, but we should need R plus 1. So it's determined by these distances, by the distances from each of those points. And we need one more, and so let's just say from the origin. It's determined by these n plus 1 distances if it's in the span of these n points. Okay, so that was all I wanted to say. Yeah. Okay, so how does one prove this? And that's, yes, that's, as I said, that is basically the mathematical fact underlying this picture here, GPS, right? So, and again, everything is going to be coming from Gram matrices. So how would you do this? This is the principle that somebody must have told you. It's much better to work not with norms, but with norm squares. Right? So, because then you have inner products and you have bilinearity and you can do nice things. So suppose since y is in the span, so let's write down, say, y equals, just keep the same notation, Cj, Yj. Right? Fine. Now, let's look at the inner products. So, take the inner product with the yi's. So, yi bracket y or y bracket yi, either way, is summation Cj and then yi bracket yj for all I. Right? Which means that this vector, the vector of y1 bracket y, y2 bracket y, yn bracket y, this vector, this is a column vector, this is equal to how much? It is basically the Gram matrix. I'll just say G now, I'm going to stop writing Gram. It is equal to this. Right? What do I need to determine? I said y is uniquely determined by this thing. So what do I need to determine in all of this? The coefficient vector C. Okay, so I don't know these guys either. What I do know, I don't know these guys either. Okay, I don't know anything. Fine. What do I know? I know these distances. I do know these vectors. So I know this guy. This I know. Fine. I know the vectors y1, y2, yn. So I know their inner products. Fine. Okay. Maybe I should have said that by the yj's and the positions. I do know this guy. Fine. What else do I know about this matrix? It's not singular. So I can definitely say that this vector is equal to this inverse times that. So if I knew, so I know this, I know the Gram matrix because I know these vectors. So I know the Gram matrix, so I know its inverse. I don't know these guys. So if I know these guys, then I can calculate. So by the lemma, the C vector equals the Gram matrix inverse times the vectors of y, yj. and I know the matrix, so I know the inverse, so it's enough to understand what those guys are. So how do you calculate these guys? Square the norm, yeah. Basically what you have to do is, and there's a name for that identity. It's exercise for you and it's an exercise for me. Yeah, so now, so enough to use, enough to determine the y comma yj. I can write the j correctly from the given data. And this is called the polarization identity, or the real polarization identity. And this simply says that if you want, let's say this guy, well, let's write this down. So we can say that how much is this? Let's see. So y square equals, what do I want to do? Maybe the other way, y minus yj square. Basically, a minus b square is a square plus b square minus twice y minus 2ab, right? So, and since I know y, and I know this, and I know these are the diagonal entries of the Gram matrix, so I can just take all of those there and I get my missing coordinates. Okay, fine. So, yeah. I mean, the polarization identity, I think what it says is this guy equals the rest of it divided by 2, as far as I remember. But yeah, it's basically a square, a minus b square, or a plus b square in inner product spaces, not in real numbers, but in any inner product space. Okay, so once you have this thing, so therefore I can determine this guy from the given data and therefore take the inverse, and that's what it is. Okay, so this is again to my primitive understanding of GPS and the use of Gram matrices in doing GPS. Okay, any questions? Please feel free to ask questions. So,
we know a solution exists just for the fact that we can invert the matrix, but we can to calculate the inverse to make life easier. That's what we do.
I mean, yeah, we know a solution exists. I mean, a solution exists is fine, but the question was to uniquely determine C, and so you would have to do all this. Yeah, we know the matrix is invertible by the lemma, right? Okay, great. So, okay, very good. I think we are reasonably on track. So okay, so the next, so that is, this is some sort of maybe first part of Gram matrices. So some synonyms like PSD matrices and correlation matrices, and one basic application to like GPS kind of thing. So now the next application I want to tell you, or almost basically the rest of the entire lecture, is to do with metric geometry, so metric spaces. So has everybody here seen metric spaces? I hope. Even in the first year, I think they start with baby Rudin still. Yes, okay. That's what we started with. So, oh. So now let me get to the first part of the abstract, which was about, if I give you a finite metric space, so let's write this down, x equals x naught, xn, and b is a finite metric space. Okay. And what, so in the early, not very early, maybe in the early 1900s and first half of the 20th century, people were interested in trying to somehow do something called metric geometry. So metric spaces were introduced in the early 1900s. And some of the names associated with this are Burkhoff, Rechet, Menger. Am I missing somebody? Hausdorff. Yeah, so in the early 1900s, in the early 20th century, these were some of the people who worked with, who introduced and did early work on on metric spaces, not just finite ones. And so, and then people were interested in not just metric geometry, so developing the properties of metric spaces, but also metric embeddings. Okay, so for example, Frechet had this early result in 1910, I think, Frechet's theorem. And he said that every single finite metric space of with n plus 1 points embeds in Rn when I say embeds, I mean you have all seen isometry, mapped from one metric space to another such that the distance is exactly the same distance between them. Right? So embeds isometrically into Rn, but not Rn with the Euclidean norm, Rn with the sup norm. So n plus 1 points goes into Rn with the sup norm for all n. So I won't specify that this has a n plus 1 point. This is going to be assumed, notation is fixed from now. Okay, so xd embeds isometrically into Rn with the sup. Fine. So in fact, this was late. So okay, one of the proofs of this basically is, I'll just tell you the name of the theorem, or there was some other mathematician called Kuratowski who extended this from finite to like even more general infinite metric spaces. Okay, but with the same exact map that works for infinite metric spaces works for finite metric spaces as well. So if you just Wikipedia for Kuratowski embedding and whatever function, whatever embedding you see there, if you specialize to X a finite metric space, you get exactly this embedding here. So that's one easy proof of this theorem. Now, it gets embedded into something called, I think, continuous functions on X. So functions from X to R. So if you look at function or and for infinity, then one less doesn't matter. I think that's roughly the idea. But there is a way to make that precise. If you see that map, that basically means that. So the way it embeds is the following. If you specialize that particular map, it will say it embeds into continuous functions from X to R. And there is a specific restriction also. It's not just all continuous functions. It's all continuous functions where you fix a base point and the value at that base point has to be 0. So the non-standard or non-canonical part of it is you don't know which base point. You can choose any base point to start with. So in some sense, what it's saying is Kuratowski embedding phi x naught. For any choice of x naught in X, you can define an isometric embedding from xd into continuous functions of X with the sup norm. That's the general statement of Kuratowski's theorem. But furthermore, such that vanishing at X, vanish not just any continuous function, but any continuous function that vanishes at X naught. The what? Oh, I don't know. I never thought with algebra in this, but you can check. And so anyway, the point is if X is finite and you want to look at continuous functions on X, Then if x has n plus 1 points, what is the set? Of course, it's a finite metric space, so it's discrete. So what is continuous functions on x, that x? R to the n plus 1, because there are n plus 1 points, so R to the n plus 1. What about continuous functions that vanish at a point? That means one of the coordinates is 0, so basically that's Rn, and that's what's here. So that's why Rn and not Rn plus 1. So if you look at this map, it exactly vanishes at a point. You can choose which point. Either way, some coordinate will have to be 0 for the entire space, and so it maps into Rn with the sup norm. So that's an easy theorem. Now, can you improve on this? Can you improve on the n? Can you do that? Because you already know that, of course, it can map into Rn plus 1 maybe with the sup norm, but now you're saying it maps into Rn with the sup norm, and here is an explicit isometric embedding. Can one find an isometric embedding with fewer points, with fewer coordinates? So how about for, let's say, n equals 2. So 3 points. We are saying that every 3-point metric space embeds into R2 with the sup norm, not the Euclidean norm. Can a 3-point metric space can every 3-point metric space embed into R1 with the sup norm? Yes or what do you feel? Yes or no? No. What triangle? Huh. Every 3 points can be placed in a triangle. You have to say something more about the triangle. If you're saying no, you have to give me a specific triangle. It's only one triangle you can give me, equilateral triangle. So yeah, if you take an equilateral triangle, there is no way you can embed it in R1. You can think about this, but it's fairly easy to visualize in the mind. Yeah. If you have 2 points and a third point, then they have to be in a line, and then these two cannot be at the same distance as half of the distance. So yeah, so for n equals 1, no, n equals 2, already this cannot happen. Remarkably, for n bigger than 2, it can happen. So this again, I did not know this until like 2 years ago, or maybe 4 years ago, something. But yeah, so so can n so can x embedding into R n with the sup norm be reduced? No for, let's say no if n less equals to. Well, if n is less than 2, then you can't even go into R to the 0. So 0 is a 1 point. R to the 0 is a 1 point space. You can't even have 2 points in there. Yes. You can. And I don't know the best possible answer, but what I do know is, so there's a theorem by Witzenhausen. Witzenhausen's theorem says exactly that. X comma d embeds for isometrically into R to the n minus 1 comma sup norm for all n bigger than 2. So you can't embed in the line, but you can embed in the plane and height. And I don't know, is this the best possible? I do not know. And not for all n again, but let's say n is like 2024. Then it can go into 2022, but can it go into 2021? I don't know. I was too lazy. Huh? There's nothing to do with primes. This part is purely like, basically in the way this proof works. So the way this proof works is, the first you prove it, he gives an explicit map from R4 for a 4-point space to R2 embedding. And then he says, I don't know if he says or somebody else, maybe he said it. Once you have, then you basically do induction on the dimension, on the size of the metric space. Once you have this thing, then given one more point, you can first, I think, put 0 at the last coordinate and then figure out a clever point where the last coordinate is non-zero. So first, if you have 4 points, once you're given one more point, take those first 4 points, let's say, put them in R2 comma 0, and now take the fifth point and then put it in something where the third coordinate is not 0, as far as I remember. And then once you have that, now how do you choose such a fifth point coordinate? That the proof, so yeah, the induction step here, just as I said, so the base case of n equals 3 is explicit, like explicitly given that, and then the induction step is to cleverly come up with an extra point with the last coordinate non-zero, and this uses something called Helly's theorem, which I think maybe you may have seen in or somebody may have seen in probability. I don't know if Yogesh may remember. Have you seen something called Helly's theorem? I mean, it's maybe part of the proof of that. Like if you have some, I think one part maybe some, but I think something like it says if you have a bunch of if you have a bunch of intervals, every two of which have an intersection, then all of them have a common intersection. And similarly, if you have a bunch of convex subsets of Rd, where every d plus one of which have an intersection, then all of them have a common intersection. That kind of Helly's theorem. Yeah? So that some of that gets used in constructing this point. Like the point is, you want the last. So each coord somehow you want. Let's see. So I have these first 4 points specified. I add a 0 coordinate at the end. I have the fifth point, and I want to have a non-zero third coordinate and other coordinates. The way you do it is to somehow use distances of this to each of them gives you some inequalities. Distance from the fifth point to the first gives you inequality, distance from the fifth point to the second gives you inequality, and so on. And you want a simultaneous solution to those inequalities because that would give you a fifth point. And the simultaneous solution is something that lies in the intersection of all these inequality systems, and that is where Helly's theorem gets used. So this is completely vague, but roughly speaking, that's how you want to solve a system of inequalities, and you say that a solution exists, a common solution exists if the intersection of various balls is non-empty, and it's non-empty because every few balls intersect in non-empty. That's Helly's. Okay, so anyway, so yeah, so Witzenhausen, of course, I think was maybe even 1980s, so something like this, so much later than Frechet and so on. But anyway, there was this big rush, like the gold rush. Everybody wanted to work on not everybody. Many people wanted to work on metric geometry, metric embeddings, and so this is one of these early theorems that says that every finite metric space is a subnorm metric space. In fact, every metric space, maybe every separable or something metric space, can be realized as a set of functions with the metric being the subnorm. So naturally the question was, can you ask about metric spaces with the Euclidean metric? If I give you a finite metric space, when can you answer if it is Euclidean or if it isn't? Can you definitively say, right? So, and the answer turns out we can always answer if a metric space is Euclidean or not. But let me say that. So the next question, therefore, is how to tell okay. What does Euclidean mean? It means it embeds inside R to the R with the two norms, the inner product space. That is the question 1 maybe. And question 2 in the line of Witzenhausen's theorem is, suppose I can tell it's Euclidean. What is the smallest dimension? Right? If yes, and this was answered by in 1935 by somebody called Schoenberg. And basically, much of what I have been doing in the last 10 years in the matrix analysis side is to look at Schoenberg's theorems, so one kind or another. Schoenberg was amazingly creative. So, as I said, he had a lot of contributions to matrix analysis, to positive semi-definite matrix theory, and I should be able to tell you some of that. Uh, he also had contributions to metric geometry, which I will now tell you. He also had contributions to something called totally positive matrices, which are these are matrices. If you take any 3 rows and any 3 columns, or any 4 rows and any 4 columns, the determinant is positive. So every entry is positive. All 2 by 2 minors are positive. All 3 by 3 minors are positive. Similar. Those are called totally positive matrices. Schoenberg had a lot of lot of contributions to that. Fine, and to not just finite matrices, but infinite cross infinite matrices as well. Like matrices are functions from m cross n to r. You can do functions from z cross z to r. These are just bi-infinite matrices. You can do functions from r cross r to r, like uncountable cross uncountable matrices. Those are the ones that are totally positive or negative, are called Polya frequency functions, and so on. So Schoenberg had a lot of contributions to those guys, and out of that last total positivity, he invented what are called spline functions. So spline functions are very useful in numerical approximations, and Schoenberg was also the inventor of that and pioneered some early work in that. So a very versatile person. Let me write down the statement and the notation. For this I need a definition. Sorry, oops. So where should I write this definition down? Yes. Very good. The X is there, and I will write down a matrix from X. Okay, so definition. The modified Cayley-Menger matrix, and this bad. Fine. So X has n plus 1 points. Now, as we know, as you have seen, for any metric space, the entire information about that metric space is given in the distance matrix. You just have, if you have distance xi, xj, that has all the information about the metric space, because that's all the data you have. This one is, that is a n plus 1 cross n plus 1 matrix. This matrix is going to be n cross n. So here is the ijth entry. I comma j go from 1 to n. Okay, I don't know if that's it. di0 square plus dj0 square minus dij square, where dij obviously is distance from xi to xj. And I and j are positive, so they go from 1 to n. X is x naught through xn. What happens if I take I equal to 0? Okay, first of all, this is real and symmetric. That's it. It's real and symmetric. What is it on the diagonal? When I equal to j, it is twice the distance of I0 square. This plus this equal to this, and this is 0 when I equal to j. What happens if I take I equal to 0? I get d0 0, which is 0, plus dj0 minus d0j. So you get 0. So if you are welcome to, therefore, suppose that it's n plus 1 cross n plus 1 matrix, but then the first row and column are just 0 entries. Because it's symmetric, and if I equal to 0 gives you 0, then j equal to 0 gives you 0. So there's nothing gained extra by taking the full 0 to n. You just pad it by a row and column of zeros. So we tend to ignore that, and we say this is a one dimension smaller matrix, square, real and symmetric, and this is the modified Cayley-Menger matrix. Okay, so this matrix will also show up again once now and once at the end of the talk. So Schoenberg's theorem says the following: X is Euclidean if and only if, and Euclidean means this, embeds isometrically into it. If you take the modified Cayley-Menger matrix of X, this is positive semidefinite. So somehow this goes from matrix to matrix. And the second one is, but positive matrix. And the second one is, suppose this is Euclidean. So if yes, what is the smallest dimension? The smallest R is simply again the rank. So again, we come back to the original, that's all erased. We come back to the original set of observations, where somehow the smallest decomposition I could take for a positive matrix to be B transpose B was the rank of that matrix. I never proved anything about that, but that was what I said. And the reason why this smallest R looks, the statement looks similar, is because it is the same. Let's see why. Okay, so let's do the easy part of this theorem. I mean, the other part is not too hard, but longer. Let's do the shorter part of this theorem, maybe. And the shorter part of this theorem is exactly going to be, again, the polarization identity. Let's see why. Well, in some sense, well, okay, let's see. So, proof of one part. If X is Euclidean, then let's check that this is PSD. Let's look at the ijth entry. So di0 square plus dj0 square minus dij square. Now suppose X is Euclidean, meaning X isometrically embeds into whatever, then I can think of those vectors, those points X's, I can identify them with the images in R to the whatever, in Euclidean space. The moment I can identify them, what is distance of I0? It's Euclidean distance. So Euclidean distance is norm square xi minus x0. Where again, maybe I should say yi minus y0, where y is the image of x, but you know what I mean. Identify the x with their points, with the images. R to the whatever. I don't care what, but yeah. Plus xj minus x0 minus xi minus xj, but of course I'm going to write this down as xi minus x0 minus xj. And so now you have a square plus b square minus a minus b square, and that is 2ab. So this is the ijth entry of the modified Cayley-Menger matrix, and so that means that Cm prime is a Gram matrix, and now you're done. That's one half of it. The other half is not much harder, but it takes more sort of time and effort to write down carefully. Okay, the smallest rank is this rank. Well, why? What do we know about the rank of any Gram matrix? An upper bound for that rank? Is the dimension of the space it comes from. Yeah, that is harder, but let's not get there. No eigenvalues were harmed in this talk. So let's say if these vectors are coming from some space, this question mark. So the rank of this of the Cayley-Menger prime is less equals the question mark, the question mark, right? Because it's a Gram matrix. Now, if R is the minimum, if R is the smallest question mark, question min, if you will, then what can you say? Well, actually, the converse is also true, right? If you get a Gram matrix of some rank, then you can get vectors from that dimensional space. So the moment you could, so if you could get a Gram matrix from a smaller rank, I mean, if you could create them from a smaller dimensional space, the rank would basically come down. And that can't happen, so it can't be strictly less, and therefore it has to be equal. So I won't write all that down, but yeah. That's all I'll say. So this is Schoenberg's theorem, and so it talks about when is a metric space flat. That was one of the questions I mentioned in the abstract. Okay, now before I tell you about when is a metric space spherical, that was the next question I mentioned. Let me tell you something else about, let me tell you a different characterization that Schoenberg also proved. This was in 1938. So what he said was the following. Let me just, this one I need to. So first of all, he made the following observation, and he made it using some very difficult. This is which page am I on? Okay, I'm basically exactly halfway through. Well, let's see. So what he said was the following. Okay, I need a definition first. So okay, what did we see here? We saw that by taking some by taking a distance matrix and applying some transformations to the entries of the matrix, you get from a metric space to a positive semi-definite matrix. Yeah. You can ask, why can I do so without applying any transformation? Well, no, okay, not without. So what Schoenberg's theorem says is you start with a distance matrix Dij, and if the metric space is Euclidean, then if you convert that matrix to this guy, you get a PSD matrix. Okay. Now this is not exactly an entry-wise transformation of the distance matrix. You are squaring each entry and then you are doing some weird things to it, right? You are adding something and subtracting something from there. So fine. So maybe I'll just define. I'll tell you the other one then. Fine. You can check that this matrix. नहीं जाने दो. I won't tell you that. So one more complicated notion. Maybe I'll ask the question. Which functions send applied entry by entry to a distance matrix on a metric space, not on, from, I guess. PSD matrices. Okay. And so the definition is such functions are called, maybe let me not call x. X was fixed to be a finite metric space. Let's call this y. So y is some metric space, any. It can be infinite, it can be finite, uncountable. Such functions are called, are said to be. Okay, maybe I'll leave a little space here. Are said to be positive definite. So in those days they did not like the word semi, it seems. So this definite just means positive semi-definite, and what we call positive definite, they would call strictly positive definite. So the inequality is strict, so strictly positive definite. But for them, definite means what we call semi-definite. These are called the positive definite functions on Y. Okay, so now, so what are these functions? Which functions f applied entry-wise entry by entry to a distance matrix. So what is the domain of such functions? Domain of the function, I am applying it to entries of the distance matrix. It's not y cross y, it is applied to distances, it's applied to entries here. Entries of a distance matrix are 0 infinity, not even r. And if you are going to get PSD matrices, then at the very least you want to say maybe r here, just to be safe. But most likely this is also going to be 0 infinity, right? Anyway, so yeah, at least 2r. So these are the, so now what are the functions? Okay, do we know examples of such functions which are positive definite even on Euclidean space, and therefore on every Euclidean metric space that embeds into Rn? So yeah, sorry, it means you take a metric space, you take any choice of points in that metric space, right?
How do you define infinite PSD matrix? You said y can be any.
No, y can be infinite, but okay. Maybe I should say that here. Okay, yeah. So here is an example of a distance matrix. Here is an example of a positive definite function. If you take R1 with the sup norm or the L2 norm, it's the same norm in one dimension. The Gaussian density is positive definite. In fact, it's strictly positive definite. Well, if you don't repeat points. So how do you do this? Well, you have to use the fact. So okay. Have you seen matrices of this form? Whatever. How about what are they called? They are not. So the first one was van der Waals matrices. These are called generalized van der Waals matrices because the powers are not consecutive integers. So in general, you have these things called. So if I give you something like xi power yj, I and j goes from 1 to n, let's say x, and of course the bases are all positive and strictly increasing. Let's say I goes from 1 to k. Let's use a different number of rows and columns. And the exponents can be real because once you have positive numbers, you can raise them to any real powers. So these are called generalized van der Waals matrices, which I will not write down. Too long words. I will abbreviate them by GVMs. Okay, fine. So the lemma, which was proved by Gantmacher and Krein in the 1930s, it's a very clever proof actually. Is that these guys are totally positive. Meaning you take any 3 rows and any 3 columns, the determinant is positive. And if you look at any 3 rows and 3 columns of this guy, of a big matrix, it's going to look exactly like this. And the 3 rows you choose are the xi1, xi2, xi3. The 3 columns you choose are yj1, yj2, yj. So it looks exactly like this. So it's enough to prove that the determinant of every such guy is positive. Then you prove that the determinant of every submatrix is positive because they all look the same way. So yeah, so basically what they said is the debt of it's a very clever proof, and yeah, I can tell you a source. I mean, I have lecture notes online, and this is in the lecture notes. But I think I will not go there because that takes 20 minutes in itself, or 10 minutes in itself. But yeah, okay, so now once you have this, why does that imply the Gaussian density is positive definite on R1? Because, okay, I will not touch this part. Okay, so proof of that lemma. What would you do? So let's take positive definite, right? What does that mean? It means that I need to take a finite distance matrix. So I need to take finitely many points in R1 and look at the distance matrix. So our points in the metric space were called, I don't know, but I'll call them y1, y2, yk. So let's look at now what are we doing? What is the distance between the points? Mod y1, right? So you have to take the absolute value. Wait, and now we have to apply this function to every one of these guys. So from this you get to the matrix, which is e power minus, I can remove the mod because I'm squaring. And the claim is this matrix is positive semi-definite. And again, to say that some matrix like this is positive semi-definite is the same as saying every principal minor is non-negative. You take 5 rows and the same 5 columns and you get non-negative. But if you look at this matrix, again it's of that kind, that if you take 5 rows and 5 columns, it will also look like this matrix. yi1, yi2, yi5. But because the columns are the same yi1 to i5 are there. So therefore, it's enough to show, to prove this lemma, it's enough to show that this matrix has non-negative determinant for every choice of k. Then the smaller choices of submatrix is the smaller k. So suffices to show that the depth of this guy is non-negative. Let's give this matrix a name. Let's call it C, let's say. Okay, so enough to show. Now, how do you show this? You again use the fact that you know how to expand a minus b square. So note that before you talk about the determinant of C, let's factorize C itself. So C is going to be the following. I claim it's going to be the following. It's e power minus y1 square, e power minus y2 square, e power minus yk square times something times again the same matrix as first. Okay, and literally it's just, this is e power minus yi square, e power minus yj square, and e power plus, and the plus is very important, twice yi yj. Okay, let me call the entire this guy as xi. So this is a matrix of the form xi power yj. Did I assume that these were increasing? I did not. I should have. The moment I assume it's increasing, the xi's are increasing. Exponential is monotone. So this is a generalized van der Waals matrix. So its determinant is positive by Gantt-Marker and Krein. These two are obviously positive determinant, and we are done. Of course, if you repeat any y's, then the rows and columns are repeated, and you can easily check that maybe the compressed matrix with distinct y's is positive if and only if you blow up, inflate some of these two repeated rows and columns, it's positive. So that's just easy. So we can take WLOG, the y's to be distinct, and then you get exactly this factorization. So we are done. The Gantt-Marker and Krein. This is why, therefore, the Gaussian density is positive definite on R1. And you can check similarly that the Gaussian density is positive definite the multivariate Gaussian density is positive definite on Rk or Rr. Okay. So similarly, actually from this it follows in one line, but since I haven't told you that lemma yet, I will not tell you the proof. So I'll just say corollary. The function e power minus non-square x is positive definite okay, something is very wrong. I think no, I think this is just e power minus x squared, not non-square, right? Because remember, the domain is not y, the domain is 0 infinity. So it's a one variable function. It's for all r, not just for r1, but for all r. Okay. Why it's a corollary, I will not tell you just yet, but yeah. Or ever, maybe, we'll see. Okay, so Schoenberg was looking therefore anyway at functions which were positive definite on Euclidean spaces. And so he proved this fact, and then he derived from it this fact, but he did it using far harder, like he did some Fourier analysis and harmonic analysis and so on. Whereas for R1, the proof of this takes 10 minutes and it uses just linear algebra and very basic analysis, nothing Fourier or harmonic about it. And this is just a factorization of this. So it's very easy. But anyway, this was proved. Schoenberg did this in 1938. Ganttmacher and Klein did this, I think, in Russian in the 1930s. So it hadn't reached Schoenberg in the US. Anyway, so but there was a proof available, and so fine. So first he understood which metric spaces are flat, Euclidean, okay, and then found out the lowest rank. Next, he asked about which functions are positive definite on Euclidean space, and here are some examples of them, the Gaussian one. But you can now therefore do the following. I can say e power minus 3x squared. That is also positive definite. Why? Because I can put everything with a 3. Right? I found 3 here. I can put a 3, 3, 3, 3, 3, 3, and here I would do a 6. And that's still the same proof, and it's still positive definite on Euclidean space. So the same thing here, e power minus 3x squared. Fine. Okay, so therefore, so let me now write down Schoenberg's theorem, really. So, theorem by Schoenberg. One was that, yeah, so, okay, I want to multiply or divide. Let me see. Yeah. Let me keep it at, like, since we are in ISI, we should respect the Gaussian density notation. For all r bigger than 1, on the Euclidean space with the 2 norm, e power minus x square over sigma square is always positive definite. And now if I have a finite metric space, let's say, if these maps again, are positive definite on a finite metric space, x, let's say, comma d, then x is Euclidean. So the only way this can happen there are no other metric spaces on which Gaussian map is positive definite. The only ones are Euclidean spaces, nothing else. Again, I won't prove this. It's not hard. but I won't do this. And again, you can find this in these lecture notes that I have online. The entire proof of this, Gantt marker trine, why this corollary follows from that, everything. All that is fairly straightforward. Once you have, with all the coursework you guys have seen already, it should be enough. I judge it from what I saw in my BStat first year, which you guys must have seen more than that, because this is the math. But yeah, so the only metric spaces on which the Gaussian density is positive definite is the Euclidean, is Rn or Rk. Right? So somehow Gaussian is really closely associated with Euclidean spaces for multiple reasons. One is of course probability, but now also metric geometry. Okay, so this was what Schoenberg did for flat spaces. But now, as I said, the other thing in my abstract was about when is a finite metric space spherical. So inside the Euclidean space, every Euclidean space sits the Euclidean ball or sphere. Right? The ball is just a solid thing with the metric on that is the Euclidean metric. But on the sphere, on the circle or on the sphere, there is a different distance. There's a different notion of distance than the Euclidean one. Of course, you can say the distance between these 2 points is the distance of the line segment. But that's just boring because that all is answered by this theorem. Here is a different distance, and what is the distance between these 2 points in the spherical metric? Is the angle, the geodesic, right? It's the length of this. So let's assume, of course, the sphere is of unit length. Then the sphere, the distance is exactly the length of the arc, which actually equals the angle. That's the definition of angle is the length of the arc. What happens? This is in R2, or I mean S1 inside R2. What about S2? If I give you 2 points, what is the solid angle? I forgot all my Loni or whatever the hell this was. What cross section? Correct. Right? So exactly. So what you can do is the following. There are two cases. Either these 2 points and the origin are not collinear. It's the only way they could be collinear, and these 2 points on the sphere are minus c. So the fact that they are not means they are not collinear. There's a unique plane passing through them. Whether this is in R3 or in Rn does not matter. There's unique plane through any 3 non-collinear points. Slice the sphere of whatever dimension. Slice the sphere SR minus 1 by that plane. And that intersects it in a circle, in a great circle, because it passes through the origin and intersects us. On a great circle, which is of unit radius, you are reduced to this picture. And the points are not opposites, but even if they were, the distance is exactly the arc length. So that's the spherical distance. Yeah. I mean, you guys already said it, but this is the precise way of saying it. Either they are antipodes, define the distance to pi, or they are not, then there's a unique great circle, slice it, then you reduce to that. Okay, so this is the spherical distance. So Schoenberg again now asked, when is the metric space spherical? When is x comma d spherical? And the answer is going to be, the answer he answered this question not in terms of some matrix being positive semi-definite, but in terms of a function being positive definite, which is basically related to a matrix being positive semi-definite. But here is his theorem. And this theorem was again not in 38, but it was back in 1935. So he had already answered this question in the same paper in this journal called Annals of Mathematics in 1935, which I have erased. So question then, so y is arbitrary metric space, x is a finite one. With the angle metric, so on. And now the answer is, so what Schoenberg's theorem in 38 says is Euclidean metric spaces, finite or full or whatever, are characterized by a whole uncountable family of functions being positive definite. I can reduce that. I can reduce that to something like this. I could say something like x square over n square. I think this should be good enough. N is bigger than I can reduce it to a countable family because by continuity you can take some dense countable subset and whatever. So I can take a countable subset of these functions. They all have to be positive definite. Fine, and then Here, you require one function to rule them all, and that function is, so let me just, so this is true for some r, right? I can just do it, fine. Let me say that. I won't, sorry, angle metric. If and only if two things, If x embeds inside a sphere, what is the maximum possible distance between 2 points? 2? No, not 2. Pi by 2? Again, no. Pi, right? The maximum distance is the opposite angle, opposite end. So, sorry, not equals, less equals pi. So I need to also impose this condition, but this is again obvious. If x embeds inside a sphere, the diameter is at most pi, and a mystery function is positively definite on x, and the mystery function is not that mysterious. This is the cosine function. So let's again, I will not prove everything, but I will prove the forward direction, which is the easier one. The backward is actually in this case quite easy as well, but I don't want to get into this. Well, else. And so finally, I think it's time to return to the main player of this talk. This is slide 9. Wow, we are trailing. Okay, maybe I'll skip that part. Maybe I should. Fine. Okay, so proof of this part, proof of the forward direction. Okay, so clearly if x embeds, then this part is counted. Why is cosine positively definite? Well, take points, take y1, y2, yk. Actually, since x is finite, it's enough to show that cosine of the whole matrix is positive. It doesn't matter. Then every other matrix is a principal submatrix, and so it's. So what is the cosine applied to the distance? Well, then let's just do entry by entry, and then we can collect the entries into a matrix. How much is this? Again? Why so? Why so? Yeah, that's exactly what we know. The angle is exactly, what is it? What is the cosine thing? The angle is cos inverse of the dot product, right? Actually, so more precisely, when you study Cauchy-Schwarz, probably somebody told you, right, that when you say that x dot y is less equals norm x norm y in vectors in Rn, then that means that you can, obviously, that means that this, if you look at the ratio, let's say neither x nor y is 0, that means you can look at this guy. This belongs to minus 1, 1. And then you say that the angle between x and y is precisely the arc cosine. For any two non-zero vectors in Rn or Rr. I need to not say 0 because I'm dividing by x and y. Now, when x and y are on the sphere, if they are on the sphere, then they are unit vectors. If they are unit vectors, then I don't need this. And if I don't need this, then when I do this, I put the cosine on this side. And so all I get is the dot product, which is the x-axis. So when I collect together the dot products, I get the gram matrix. And of course, the gram matrix is positive, therefore cosine is positive definitely. Right? So that's why. So this is why you need just one function to determine cosine, and again, the only ones on which cosine is positive are the spheres, because this is an if and only if statement. So somehow the only metric spaces which where Gaussian is positive definite are Euclidean, are flat, and the only metric spaces where cosine is positive definite is Euclidean. Now, so then once Schoenberg did this, he was interested in verifying which other functions are positive definite on the sphere. Sure, cosine is positive definite, but what else can you say? Certainly the function 1 is positive definite on the sphere. Why? I claim the function 1 is positive definite on every metric space.
All one means
Because all you are doing is take any set of points, replace every distance by 1. So all you get is the all ones matrix. So every doesn't matter what the distance was, you just get ones, ones, ones. And this matrix 1 on 1 on 1 is positive semi-definite. If nothing else, you can check that this is rank 1, so most eigenvalues are 0, and the remaining eigenvalue is the trace, which is positive, so all eigenvalues are non-negative. So PSD. Okay? So anyway, so yeah, so Schoenberg was interested in understanding which are the functions, but slightly more special. He wanted to understand which are the functions which, after composing with cosine, so like f of cosine is positive. Like so f could be the function 1, then the function constant function 1 applied to cosine gives you 1. But for example, is cosine square positive definite on the sphere, or cosine cube? All of these answers turn out to be yes, but we will see that in a minute. So let me first now tell you what Schoenberg did next. So this was 1935 and 1938, and now we come to 1942, where he wrote this paper called Positive Definite Functions on Spheres. And here he's solving the question, this is the following question he's solving. So when you take cosine, right, on a sphere, what are the possible values you will get? Outputs. -1 to 1, because that's what cosine does. So which functions, and he asked which continuous functions, which let's say f from -1, 1 to r, continuous, satisfy f of cosine of whatever is positive definite on all dimensional Euclidean, angle distance. That's the question he was solving. Which continuous functions from the output of cosine to r satisfy this condition? F of cosine is positive definite on the sphere with the angle distance for every dimension of the sphere. That's the question you're solving, and here is a theorem. Okay. In 1942, Schoenberg's theorem. If a function, if f composed with cosine is positive definite on all SR minus 1, I will not write the distance, the metric, then let's use this one. Then fx equals summation then it's actually a power series. It's something much more special than infinitely differentiable. Is fxx is cxx ckx to the k for all, so clearly this function, assuming it is defined and convergent, it is clearly continuous for some ck bigger equals 0. It's a power series, but moreover the coefficients are all positive. So now the question is, which of these power series work? He said if it works, it has to be one of these. Which of these work? Do all of them work? Do none of them work? None of them is clearly false because fx equals x works. It takes cosine to cosine, so that's positive. Fx equals 1 works because it takes it to the all ones matrix, that is positive. Which ones? Do all of them work? So in fact, so the question is now which of them work? These do work. And the answer is all of them. And this was proved even before Schoenberg proved this part. This is actually the hard theorem. The easy part is to prove that all of them actually work. And let me tell you why. And the fact why all of them actually work is the same, the reason behind why all of them work is the same reason behind why this is the corollary of that, which you can try for yourselves as an exercise. I'll just tell you why this happens. Let's keep that board. I'm feeling too lazy to bring it down. So let us see how cosine square works. I claim that cosine square actually is positive definite on the Euclidean sphere. Why? Or why is cosine square positive definite? Again, by the way, you should keep interrupting if you have questions. Questions? Okay, fine. So why is cosine square positive definite? Well, we know cosine is positive definite because when you take cosine, you just get a Gram matrix. So all I'm saying is I have a positive definite function. So I take some points x1, x2, xk, xn, whatever, xn, let's say, x0 to xn, fine. From that I get a cosine matrix. So cosine applied to distance, which is exactly the Gram matrix. Cosine of dij. This is PSD. The question is, why does this imply that, let me call it entry-wise square. So if you multiply two matrices, you know how to multiply. You don't get just the square of each entry. This is, the thing you would wish maybe in high school, or I definitely wish in high school, matrix multiplication was entry by entry. Then I don't have to multiply anything. But no, you can't do that. But in this case, that is what we want to do. Just the squares. No row times column. Why is this PSD? And the answer is yes. If you take any two, not just the same matrix itself, if you take any two matrices which are PSD, then their entry-wise product is also PSD. In fact, their usual product may not even be symmetric. I think you might even have seen that. Two matrices, unless they commute, even if they are symmetric, their product need not be symmetric. But their entry-wise product is clearly symmetric. But why is it PSD? And that's called, there is a famous theorem, which was, as I said, so many years before that. So this was proved in all of them, coming from a theorem proved in 1911. So it's really quite old. And that theorem was coincidentally proved by Schoenberg's PhD advisor, who also started with SCH. And it is called the Schur product theorem. and this product is called the Schur product. So if C and D, let's say, belongs to R K cross K, are PSD. So meaning by PSD, I of course also assume they are symmetric. Yeah? Then their entry-wise product or Schur product this is not the usual product, not row times column. This is entry by entry. This is real and symmetric and in fact positive semidefinite. So let me give you 4 proofs of this. Let's see. I'll give you 3 proofs of this one. Just for fun. The first proof is just by the spectral theorem. C is summation lambda I, let's say vi transpose. Write some eigenvalue, eigenvector decomposition. D equals summation mu j, uj transpose. I goes from 1 to n, lambda i's are positive, j goes from 1 to n, mu j's are, 1 to k. I'll give you 2 proofs of this, right? I keep reducing. Yeah? Now, you know that whatever this product is, it is bilinear. It is linear in the C. If I take C plus D, then C plus C prime, I get C plus C prime. And it's linear in the D. So if I take the entry-wise product of this and that, and these are all linear things, then I get a double summation. I and j both go from 1 to k. I get lambda I times mu j because linear, so coefficients multiply. And then what do I do? The entry here was vi1, vi2. That's the 1, 2 entry. Here it was uj1, uj2. So when you multiply the two, I and j are still fixed because it is a double summation. I get vi1, uj1 times vi2, uj2. So it's the first entry of vi dot uj times the second entry of vi dot uj. So it's literally vi dot uj, Schur product, and then vi dot uj transpose. Okay, I hope that's kind of plausible, believable. But now look at this. So this is of course rank 1 in positive semidefinite, and this is because lambdas and mu's are non-negative, this is non-negative. So there's a different definition of the actual definition of positive semidefinite is that the quadratic form of this is non-negative, right? Which means if I take any like a W transpose and W here, I better get something non-negative. But well, again, W transpose W is bilinear, so I can just take it here. And then you see that this is the square of this much. So non-negative. This is non-negative. So everything is non-negative. It's a finite sum, non-negative. So this is non-negative. So that's the first proof. You're just using the spectral theorem of the Schur product theorem. And the second proof is, I just mentioned it again because sort of this is ISI, so I'm sort of like almost bound to mention it. I have to mention it. Certainly for B stats, I would like have to mention it, but well, this is still ISI, so I'll call it proof 4 because in my lecture notes I actually do write down 4 proofs, and this is the 4th of the proofs, and the proof is following. So first of all, to prove that C times D is positive semidefinite, it's enough to look at, let's say, C plus epsilon identity and D plus epsilon identity. So enough to show. Let's enough to show this is positive semidefinite for all epsilon positive, right? Why? Because when you take the limit, you get C times D as epsilon goes to 0. If I can show something stronger, then great, better. Now C plus epsilon times identity, the eigenvalues are epsilon plus the eigenvalues of C. You can check that, or you probably have seen that. So therefore, these are all eigenvalues are positive. So this is not just positive semi-definite, this is positive definite matrix. Not some function where this is non-strict. These are strict inequalities. W transpose this W is strictly bigger than 0, as long as W is non-zero. The same way this matrix is positive definite. Now here is the trick. If you have a positive definite matrix, wonderful, yes, thank you. So if you have a positive definite matrix, you can draw a random multivariate normal vector, let's say with mean 0 and variance C plus epsilon. And you can similarly draw a multivariate random vector Y with again mean 0 and D plus epsilon. Now let's and I can, let's say, assume, so draw X and Y which are independent of each other. Why this can be done, you ask Yogesh. Now suppose I can do this, right? Then let's look at, well, what do you expect this to come from? Which is x1, y1, x, whatever, k, y, k. What is the mean of, actually I don't even care, but what is the mean of this variable? I'm not claiming this variable is, this vector is normal. Maybe it is, I don't know. But what is the mean of this guy? Just for fun, it is 0 because they're independent. So exy is exey, and that's 0 times 0. What is the covariance matrix of this? Guess what? When you do the calculation, it is exactly this thing. And as you know, covariance matrices are positive semidefinite. So this is positive semidefinite for every epsilon, and therefore you're done. So modulo Goenka is sort of a little bit high level probability or random matrix, random vectors, random normal, nothing more. You can prove the Schur product theorem again. So in various different ways, therefore. Okay. Okay. Anyway, so because of why does this theorem help? Because now look at this question. Right? So which of such functions are positively reflected on the sphere? Well, if I know cosine, then I know cosine square is positive definite because, well, this for this reason. Now, can you do cosine cube? Yeah. So just take this to be the first matrix and take D to be the cosine matrix again, which will give you this ground here. This is PSD. Now, cosine square times entry-wise cosine is cosine cube. So that. Now, cosine fourth, well, you do this, and then fourth. And by induction, you get every integer power. When you raise a PSD matrix to an integer power, you get a PSD matrix. When you multiply PSD matrix by non-negative scalar, you also get PSD matrix. W transpose scalar times matrix times W is positive. Scalar is positive, so the whole thing is positive. When you add things up, again you get positive because W transpose A1W plus W transpose A2W, positive plus positive. And when you take limits, it's positive. Everything is positive. That's why the Schur product theorem was proved in 1911, and in 1925 there is these two analysts, the famous ones, Polya and Szego. I think they were both at Stanford University. In fact, they were both faculty there. When they wrote this book of theirs, they were not faculty at Stanford, but later on they both coincidentally ended up at Stanford. Anyway, in their book, they said that by the Schur product theorem, proved 14 years ago, we know that all of these functions are positive. And they asked the question, are there any others? And Schoenberg basically answered that there are none. So really, Schoenberg was actually the later story. The Schur product theorem and Polya-Szego were the earlier one, which I told to you in the reverse order. But all of these come from basically Gram matrices. Cosine gives you Gram matrices. Schur product theorem versus PSD matrices. But as we said at the beginning of the talk, PSD and Gram are one and the same thing. So all we have been doing so far with the Schur product theorem and these proofs and this, everything is just Gram matrices. Okay. So the final application then of the Gram matrix part is about Heron's formula, right? So that's the last thing to tell you about. So remember, now we come back here. So I have this modified Cayley-Menger matrix, right? I don't remember, maybe I don't know what Menger had to do with it, but let me tell you what Cayley had to do with it. And Cayley proved a very nice theorem when he was in his undergraduate, so when he was your age. The advantage was, all these nice theorems were not proved then, so somebody had to do it. So he did it. But you can still sometimes find, some math has a bunch of unknown things. Like very recently, I worked with a PhD student at IISc, and we discovered some equivalent condition to when is a non-linear space Euclidean inner product, which morally should have been proved in 1948 because everything in the proof we used was proved by 1948. But then I asked a lot of different people, Hungary and US and Slovenia and France and India, of course, England, and nobody seems to know a place where this is written down. So something that's very basic by now, very basic, but definitely everything was known in 1948, still not proved 75 years later. So, keep looking. Maybe right now you're too young, but if you pursue mathematics or any kind of research, we believe that there can be very basic results which are not yet known, and you might be able to discover. Do not believe that everything basic is known, because it isn't. Okay, so this Cayley-Menger. So what Cayley was looking at is the following. So we will now look at of X, right? But now what I'm going to now from now on, we will assume that X is a finite metric space, which is Euclidean. Oh, okay, it's going to be a finite metric Euclidean space or finite Euclidean metric space. Okay, so then this is literally just the Gram matrix kind of thing, right? Okay, so first of all, Cayley's question was, so I'll just tell you the date as well and his result. Maybe I'll just mention this. In fact, which we will justify in the next few boards. So this is some PSD matrix. Fine, that's all. We already know that. What I care about now is for Euclidean metric spaces. I care about the determinant of this. So of course, this determinant is non-negative because it's a PSD matrix. This turns out to be related to the volume. These are in R to the whatever R, so the R volume of, I think I want to do, maybe I'll just say volume, and volume in the correct dimension. So there are n plus 1 many points. Let's say they are in R to the R, but in principle I can definitely take this to be in R to the n. If there are 3 points, I can take, they need not be in R square like with the origin, but they can be in an affine hyperplane. Every 3 points uniquely that are not collinear determines a plane, affine. So I can, but then I can, as far as I'm looking at distances, it doesn't matter whether the plane is somewhere here or somewhere here or somewhere here. Distances are distances. You're subtracting. Right? So in some sense, if I have n plus 1 points, I might as well look at the n volume of the simplex. So now if I have 3 points in 2 dimensions, if I have 3 points, they form a 2-dimensional triangle. If I have 2 points, they form a 1-dimensional, we don't call it a triangle, we call it a simplex. If there are 4 points, they form a tetrahedron. And in general, this is called a simplex. With vertices x. By x, I mean the points of x. I will elaborate on this in the next few boards. But this n volume is this basically the analog, the generalization of Heron's formula in n dimensions. That's where we are going in the final part of it. Okay, so the first question, maybe before we talk about the actual formula for the volume, or question 1 or question 0 maybe even, when is this volume 0? When is the simplex flat? So for example, 3 points, when does the triangle have 0 area? Meaning when are they collinear? Right? And so this is the theorem that Cayley proved in his undergraduate days, apparently, 1841, a long time ago. If this happens, if and only if and only the xj's are affine, they're not linearly dependent, they're affine linearly dependent. Remember, they're Euclidean, so all these points belong to some Euclidean space, are affine linearly. Affine dependent just means if you look at, say, xj minus x0, so one of the points becomes 0, right? So, and you remove that 0 point, then they are linearly dependent. Or in other words, they lie on affine hyperplane. Meaning a lower dimensional subspace, but not necessarily passing through the origin. Affine hyperplane. Why? For that, we need to go back to our very first level. A Gram matrix is singular if and only the points are dependent. Right? Now, what happens here? Oh, sorry, did I mention? What did I want to say? ठीक है. Something is very wrong here. So this is supposed to be a justification. So this starts to justify this fact. I haven't told you about this fact really, but as I said, it's related to the volume. So well, the volume relation is nice enough that this is the thing is flat if and only the volume is 0, if and only the determinant is 0. Okay, now that makes more sense now. At the end, probably I'll end up breaking this board. Okay, so okay, the first inequality is the first thing is fairly, I mean, by definition, when are 3 points, let's say x0, x1, x2. When is the triangle flat? Well, if and only this and this are dependent, so that you don't get actual, like, so this goes to the, so under the, say, under subtracting x0 from it, this goes to the origins, x1 minus x0 and x2 minus x0. Now, if these 3 points were not collinear, then the triangle would have positive area. The fact that they're collinear just means because 0 is one of those points, is these two are proportional. Proportional is the same as linearly dependent. So that's roughly speaking why this happens. And this happens because, well, we know this. The matrix here is a Gram matrix. Right? The moment this metric space is Euclidean, the modified Cayley-Menger matrix is a Gram matrix. It is twice whatever, xi minus x0, xj minus x0. So xj's are affine linearly dependent if and only if these guys are linearly dependent. Vectors are linearly dependent if and only if their Gram matrix is singular. So determinant is 0. This part comes from the original lemma. Right? Just again, a set of vectors is affine linearly dependent if and only if these guys, for I bigger than 0 or j bigger than 0, these are linearly dependent, because I'm not including the point 0. But nevertheless, these two are linearly dependent if and only if these are affine linearly. Right? But these are linearly dependent if and only if their Gram matrix is singular. That was the original lemma. And that singular just means the determinant is 0. So that's why that is Cayley's theorem, which we now understand fairly straightforwardly. But obviously, this entire machinery was not around almost 200 years back when Cayley proved this. In fact, that probably was where the machinery was set up to prove this. So yeah, yeah.
So he had made matrix for this, like
I don't know. So this is this thing about doing history. you read other people's work and you read other people's accounts and you take from there. So I didn't actually see the original paper, full confession. Yeah, but no, therefore I don't know his proof in particular.
Maybe it was not worded this way.
It probably wasn't worded this compactly too. Yeah, that is also quite likely. Okay, so the next point therefore is more generally. I will obviously not prove this, but again the proof is in my lecture notes on the website. So more generally, theorem, and I could not find a source for this theorem. So again, so say x as above. And Euclidean, of course, as we assumed above, then the determinant is not, so it's related to the n volume, but in not the obvious way. It is actually the square of the n volume. The determinant of this thing is, if you look at the volume, the n volume of the delta x of the simplex, because there are n plus 1 points. So it's flat if and only the n volume is 0. Lower dimensional volumes can be positive, right? Like the one-dimensional volume of this is something, but we want the two-dimensional volume of this triangle, and that is 0. So that's why I care about the n-dimensional volume. So this is volume square. Oh god. Okay, this is correct up to a factor, and the factor is on this side. So that is the formula. If I give you a metric space, then what am I doing here? I'm not giving you the coordinates of the point, right? So we know that if you have, see, if I have a x1, y1, 0, 0, x2, y2, then I know what is the volume, the two volume of this parallelepiped, right? What is that? Is the determinant x1, y1, x2, y2. So if I want the volume of the simplex, that would be 1 over 2 factorial. Obviously, absolute value. Because, yeah, in general, if you have a parallelepiped in d dimensions, then the simplex in d dimensions is 1 over d factorial of that. So you divide by 1 over 2 factorial here, and that's what the volume is. If you knew the coordinates of the points. Here it's a different thing. Here I don't know the coordinates. I just know the distances between points. The coordinates I just don't know. Nevertheless, the volume in using distances as well is another determinant up to a factor. So again, there is some factor here, but up to that there is a determinant around as well. So somehow volumes are somehow related to determinants. Okay, the next thing is now, so okay, that's therefore this is the n-dimensional version of Heron's formula. So of course, if I make such a claim, then obviously we need to check that when I say n equals 2, then we get Heron's formula. This time I didn't break the board. For instance, that's where we will stop. Let's just verify this. Two volumes, so n equals 2. So x has size 3. Right? And let's therefore just write down. So let's say this is x0, x1, x2. The sides are a, b, and c. That means b01 is a, and so on. Okay. Now let's write down the volume square. So the area square, volume, the two volumes, the area. Now it's 1 over what? It's 1 over 2 square times 2 factorial, 1 over 16. And then the determinant of a Cm prime. Now here x is 3, x has size 3. So the modified Cayley-Menger matrix has size 1 less, which is 2 by 2. So let's write this down. So it's a very easy determinant. It's a 2 by 2. And it is what? It's d0 1 square plus d0. So a square plus a square minus, okay, this is just twice a square. And then, right, I hope so. No, ये तो 2b square होगा ना. And this will be a square plus b square minus c square. right? And when you take determinant, it is this times this, which is a perfect square, minus this times this, which is another perfect square. So you do the math. This we all like because this is the easy math. This is 2ab whole square minus a square plus b square minus c square. Now this is this plus this and this minus this. Do I have a minus sign wrong? Maybe not. Maybe I do. So if I take the plus, I get a plus b whole square minus c square. If I take the minus, I get c square minus a minus b whole square. Right? Yeah, that sounds right. Which is, so let's see. So again, now this is difference of squares. You write down a plus b plus c, a plus b minus c, c plus a minus b, c plus b minus a. And there is 16, of course, therefore 16 is by 2, by 2, by 2. And as you can see, this is exactly s, s minus c, s minus b, s minus a is the square of the volume, and therefore you get Heron's formula. So once you have 2 by 2, then even I can do the math. So I did the math. Yeah, but so this is Heron's formula, and I suppose that's probably, yeah, that's exactly a correct place to stop. 7 o'clock. So yeah, so this is, so all of these basically come from Graham matrices. That's the whole point of modified Cayley-Menger matrices of Euclidean metric spaces. And so you get Graham matrices, you get old results from the 1800s, from 1900s. They connect to the Gaussian function being positive definite, and Schoenberg's theorems. And there's a lot of connections, but somehow at the heart of all of this is this one common theme, and it, yeah, shows up in GPS, shows up in distance matrices, and in ISI, of course, we should say it shows up everywhere in covariance matrices. Okay, so I suppose we'll stop and we can meet and greet. More questions?
Okay, any other question? So we also look at given a function, is this a characterization for when
Ah,
it was, like for example, the
very nice question. Sorry, I have never even thought about this. I should have. From the dual angle, exactly. Given a space, you look for functions. Given a function, you can look for spaces. And so at the very, no, I have no idea. Nice question. Thanks. I'll look for it now, but I don't know the answer right now. Yeah. It is still active as far as I know. Quasi-asymmetric, I mean, even metric embeddings, forget quasi, is still active. And very recently, I think last year or 2 years ago, there was a paper put out by some computer scientists, faculty in CMU and some students in CMU, Columbia, Stanford. Which functions take Manhattan distances to Manhattan, so L1 to L1 basically. And they were proving something 2 years ago. So yeah, this is a vast subject, and people have, von Neumann has worked on this thing, Schoenberg has worked on this thing, Bochner, of course, has a big thing on positive definite functions, but on groups. So that's a different thing than metric geometry with groups. So the notion of positive definite functions has been around for a long time. Notion of metric embeddings has been around, but by no means complete. But somehow, I don't know, maybe it's a little less fashionable now than it used to be, whatever that means. But yeah, it's still open. Bunch of questions are still open.
I've only heard of
Hmm.
that coming.
And Roma wasn't born here,
Yeah,
probably.
yeah,
So,
answering questions about positive definite functions.
oh, I don't know. It depends. Yeah, maybe I have not studied Bromo's work myself. I know. I mean, the only one I know is Bochner did it for like Euclidean spaces and then locally compact abelian groups was some other people generalized Bochner's result. But beyond that, again, I don't know how much people have looked at. Oh, I have. Yeah, sorry. I mean, yeah, Google it. Probably you'll find some stuff. But naturally, yeah, these are metrics. So hyperbolic metric is another. This is positive. Zero curvature is flat. Positive curvature is spheres. Oh, wait. For hyperbolic embeddings, there is something by somebody called Crane. Is it the same Mark Crane? It might be the same MG Crane. The Gantmacher and Crane I mentioned. The same Crane has some works. Crane and Ihvidov. I'll write the names. I know I should know this because I looked at my co-authors and I looked at this summer. I think these are the two people to look at. Somebody else had a question.
You had mentioned to Schoenberg's 1925 result gives a idea as to how we can embed a finite metric space into a flat setting. What kind of condition?
Yes.
And you also mentioned that they had done some work in totally positive matrices, but it's more general, Z by Z or even R by R.
Yes.
So do any of those results come into play in helping show if any sort of infinite metric space can be embedded into say,
No, not that. But that's a good question. So so far I just kept telling you about finite metric spaces. You can replace the word finite by separable, countable dense subset, and pretty much exactly the same proofs exactly the same statements go through modulo 1 theorem, and that theorem is due to Menger, this Cayley-Menger. That Menger had this theorem that says that a separable metric space embeds isometrically into a complete metric space. The target must be complete. Every Cauchy sequence converges. If and only if every finite metric subspace converges into embeds into the complete space. If and only. So somehow you can, of course, if the whole space embeds, then every subset embeds. Maybe I'll write this down just to be safe. Yeah, I wrote a theorem by Cayley, so on this side, let us write down a theorem by Menger. And then say that Schoenberg's theorems, which were all for sphere, when does something embed into a sphere using cosine, or when does something embed into flat space using the modified Cayley-Menger matrix. The same wording goes through for separable metric spaces, but now you would say that it doesn't embed into the finite dimensional sphere or the finite dimensional Euclidean space. It embeds into countable dimensional Euclidean space. Okay, so I'll maybe say, I won't say that because then I don't know how much time we have. I'm glad to say it, but let me first say Menger's theorem. I should know when this is, but again, it's in the precise year is in my lecture notes. Say x comma d separable and y comma d prime complete. Then x d embeds isometrically, but I'll just suppress the metric with the associated metrics if and only if every finite subset of x embeds isometrically in Y. That is Menger's theorem. Okay, so that is now using this. If you look at Schoenberg's theorem, so of course, if you have if you have a separable metric space, right? Let's say that theorem with the modified Cayley-Menger matrix. So this is actually what Schoenberg proved in 1935 for both flat space and spheres. So X separable isometrically goes into what? Well, now, if X has infinitely many points, it is not. You should not expect that it will sit inside R to the 5. Infinitely many points. The span can be much bigger isometrically and so on. So it has to sit inside R to the infinity. But the problem is, what is R to the infinity? So with the square norm. So the point is, R5 is 5 coordinates, and then you add up the sum of squares. R6 would be 6 coordinates and add up sum of squares. R5 sits inside R6 because the 6th coordinate is 0. So you can you can in principle think of an infinite sequence, real sequence of square summable vectors with finitely many non-zero coordinates. That's the union of the RKs. So the naive way to say R infinity would be just take the union of R, R2, R3, R4 because, but that space is not complete. So you can't apply Menger's theorem. The way to apply Menger's theorem is to sit inside not R infinity, which is just the union of Rk, or R bigger equals 1. It is to sit inside L2 of R, meaning the square summable sequences. Now this is a complete Hilbert space, and here infinitely many coordinates can be non-zero, but the sum of squares is finite. So this happens, X is separable if and only this happens. So X separable matrix space isometrically embeds into Euclidean space or Euclidean Hilbert space if and only if for all finite X prime containing X, the Cayley-Menger modified matrix of X prime is PSA. Why? Because it's the same by Menger's theorem as saying every finite subset X prime embeds into Hilbert space. But if you have 5 vectors embedding in even in infinite dimensional space, take the finite dimensional span of them. So those 5 vectors embed in a finite dimensional space. But if they embed in a finite dimensional space, then this happens. So that's if and only if there. So between with Menger's theorem and Schoenberg's original theorem, you get Schoenberg's separable theorem. And the same thing for spheres. A separable metric space embeds into isometrically into a Euclidean sphere. If and only if cosine is positive definite, that doesn't care about any finite subset. And the diameter is less than pi. But there it doesn't embed in the Euclidean sphere, it embeds in the Hilbert sphere, which is a set of all possibly infinitely many coordinates are non-zero, square summable sequences whose sum of squares is 1. Again, this is the closure of the union of S infinity. But it's the closure. You need to take possibly infinitely many non-zero coordinates, as long as the sum of squares is 1. So Schoenberg's spherical embedding theorem and Schoenberg's flat embedding theorem are both worked out in the same paper, and not just for finite spaces but for separable spaces using Menger's theorem earlier. That's about what I can say.
There is nothing else.